Welcome back to another crash course where I pick a topic and break it down into digestible information that you need to get started with it. And today we're going to be talking about IP addressing and some of the components that go along with this. You could also think of this video as kind of a crash course on the concepts relating to a home network. Or in other words, when we talk about routers, modems, and internet service providers, this video will kind of give you the background information on how all of that works together to bring you internet. There are no prerequisites for this particular course. Everyone should be able to understand it. And it's going to be great for anyone who is maybe troubleshooting or learning how to set up a home network and wants to get some background information on how it all works together. I will say that we're not going to be covering like specific devices, like you should buy this router or that router. I'm not going to be covering any of that, but it will give you kind of some theoretical knowledge behind those particular devices. This is also great for any web programmers or beginner network engineers because these concepts are kind of rudimentary for those specific fields. We'll cover a variety of topics, but the one that I wanted to add in here that I feel like a lot of explanations of the home network does not really cover too much is what your ISP actually does. Now, these are some really big companies that make billions of dollars on an annual basis. And so they're not just selling you internet. They have many different services to offer. And so sometimes it gets a little confusing. You know, they offer me internet, but they're actually doing so much more. So, how does it all work? So I'll be going into that. And then we'll cover the more technical concepts like DHCP, subnet mask, and kind of the protocol of IP addressing. So I am going to start off by breaking down what Charter Communication Incorporated does. The reason that I chose this particular company, also known as Spectrum, they kind of just rebranded, is because it is the ISP that I use. Now, I don't use this because they're the best. I use this because they're available to me, and quite frankly, they're the only ISP that's available to me where I live. Now, you might say, why is this the case? I thought the internet was global. I thought the internet was available to anyone, anywhere. Well, this is not the case, and ISPs actually operate in specific regions. This map right here, I pulled from this post on Vox.com. And it was actually written by a guy named Timothy B. Lee. So that's kind of funny because Tim Berners-Lee was quoted the founder of the World Wide Web. But it's not the same guy. Nevertheless, it is a very interesting post. It kind of shows how the physical infrastructure of the internet evolved. Now, going back to this map, you can see that all of these ISPs kind of dominate a specific region within the United States. All of these companies right here kind of connect together. I'm not going to go into the dynamic of how this actually happens, but they all have their physical infrastructure, namely telephone wires. That would be one case. You have like cable boxes and even fiber optic cables. So if we go over here to this really cool submarine cable map, these are all the fiber optic cables, which is by far the fastest way to transfer an internet connection or signal between one place and another. And you can see that there's actually cables, fiber optic cables that are under the ocean that connect the world together into what we call the World Wide Web. And so this is a really cool interactive map where you can kind of click on different routes and see where those cables are located. So I'd highly suggest you check this out, just play around with it. But going back to the original point, you can see that these ISPs all kind of work together to create what we know as the World Wide Web. Now, all of these ISPs are going to sell multiple types of services, and internet is just one of those services. So for our example, which is Spectrum, if we go back to a little snippet of their 10K or their annual report for 2018. So if we look at what they're spending their money on, you can see that they're actually spending about $6.7 billion just in 2018 on physical infrastructure relating to these networks. Now, I can't break these numbers out into internet specifically, but if you think about what goes into creating the internet, that's going to be telephone wires, so those cost money to own. You have cable boxes, you have modems, you have fiber optic cables, as we saw in the submarine cable map. All of these things cost money to own and to set up, and so these ISPs have to invest in those resources. So your internet service provider spends billions of dollars on literally just wires and modem boxes and cable boxes, all that fun stuff. The reason that they do that is because these are essential to getting internet into your home. Now, in this diagram, you see on the right is the World Wide Web, which is nothing more than a bunch of wires that are owned by one of the internet service providers, which sits here in the middle between your home network or the local area network on the left and the greater World Wide Web. Now, the signals that are going on here on the right are considered analog signals, or in other words, the electrical signals that are being transferred on these fiber optic cables or telephone wires are just frequencies. Now, as you know, you probably know, a computer runs on bits which are ones or zeros. So this is what we call binary code. And in order to get these messages from one computer to the next, they have to be converted into analog signals and then back into digital when it reaches the next computer. So the cool thing about these different wires is you have different frequency ranges, and it's pretty easy to separate the difference between like a phone signal frequency and an internet frequency. So this is where the topic of broadband comes in, because we now have the ability to actually have two different channels or two different frequency ranges that separate out our internet and phone signals. So previously we had to dial up to the internet, or in other words, if we wanted to connect our computer to the internet, we'd have to devote our entire connection to just the internet, and we wouldn't be able to use our phone at the same time. But nowadays, we've got broadband, which allows us to have internet signals and phone signals running through the same telephone wire into our house. These signals get into our house and are converted from analog signals into digital signals by what we call a modem. So this could be a single box that is connected via coaxial cable. So basically you connect one of those coaxial cables to the modem, and then you connect that to your wall, and you've got the internet signal traveling from the telephone wires as analog signals into the modem. The modem converts those into digital signals, or ones and zeros, and sends them over to the router in the form of Ethernet. Once it reaches the router, this is where we start to get into the concept of IP addresses, network, subnet mask, and DHCP servers. Most people understand what an IP address is in general, but I wanted to go through and kind of get the background on that and a brief overview of how we convert an IP address to a binary number. So an IP address can either be in the form of IPv4 or IPv6. These are two just different protocols. And the reason that we have these is because we're actually pushing up against the limit of 4.2 billion different combinations for a 32-bit IPv4 address. 64-bit addresses would be IPv6, and there's about 1 quintillion different combinations there, which is more than the number of grains of sand on this earth, assuming that my Google search was completely accurate, because I'm not sure how you would count the number of grains of sand on earth. But nevertheless, there are plenty of combinations in the IPv6 protocol, so we should be good for the foreseeable future at least. And what an IP address is basically something that locates a particular device on the internet. Now, most people think of an IP address as a locator for a given website, but if we remember, a website is nothing more than a particular computer hosting a web server on it. So it's really just locating a device, and then that device is hosting a website on it. So an IP address is really just a locator for any given device on a network. If we wanted to kind of see this in action, we can go over to our terminal. Let me switch over there real quick. And we can type in this command that's available on a Unix-based operating system called host. And if we give it an address, so for google.com, it gives us some information about that address, and it shows us a bunch of mail servers, and then it shows us the IPv4 and 6 addresses for Google. So let me copy this address and take it back to the browser that we're in. Let me just open up a new tab and paste that in there. If we press enter, it's going to resolve to google.com, and so that's kind of just showing you how you can use these IP addresses to resolve a given computer. Now, obviously, we think of websites in terms of domain names, and those get mapped into IP addresses through DNS servers, but we're not going to be talking about those DNS servers in this video, so I don't want to get into that topic because it's a pretty involved one. Now, we can also look at our own IP address, so we can type in ifconfig on Linux or Mac, and when we press enter, you can see there's like this middle record right here, this ENX00, etc. That is the computer that I'm on right now, and you can see the iNet and iNet6, or in other words IPv4 and IPv6 addresses for this computer. So that's just kind of how you find your own IP address. And now we can get into how we resolve an IP address into binary notation, because this is going to be essential for us understanding how our local area network works and how we get the internet service provider's internet and distribute it to all the devices in our local network. So given this sample address right here, I just made this up, it's nothing of significance, we can resolve this into binary notation with the following method. As you see below, I'm kind of highlighting these first 8 bits. So the 192, that is considered 1 byte, and a byte has 8 bits within it, and each of those bits kind of holds a different identifier. So we walk from right to left and say 1, 2, so that's double 1, and then 2 times, or double 2 is 4, and then 4 doubled is 8, and then so on and so forth, all the way up to 128. And if you work out the number of combinations you can have here, it is exactly 256. So our numbers can be, in each of these places, we can have from 0 to 255. Notice we're not going from 1 to 256, 0 to 255. And the way that we calculate this is by just adding and multiplying. So we can start here on the left, and we say 128 times 1 equals 128. So we do that, plus 64 times 1 is 64, so that's 192. And then we walk down the line, but these are all zeros, so 32 times 0 plus 16 times 0, so on and so forth, is going to equal 0. So our first number is 192, and you can see how we can resolve this through each of the next bytes of this IP address. So in other words, we have a 32-bit IP address, or this would also be equal to 4 bytes for this IP address. So that's just an overview of how we convert to binary. I would recommend just typing in IP to binary converter and going to something like this and pasting it in. It's a lot quicker than trying to resolve it on your own. The reason that I went through this little background on IP addresses is because your ISP provider is going to assign your network, so your entire network, an IP address and a subnet mask. We'll get into what the subnet mask is here in a second, but just know that you have only one IP address for your entire network. So think of it, a nice way to think of it, right or wrong, is your router is given a single IP address, and then it somehow figures out how to take that one IP address and somehow convert that into multiple IP addresses for each of the devices in your network. And this is how that is done. And by the way, this screen right here, this is just from my router's interface. I just wanted to pull it up here to give a practical example. I have a TP-Link router, and I can see my IP address and subnet mask that my ISP assigned me through this interface. Alright, so how do we calculate the different IP addresses for each of the devices in our network? Obviously, we've got to have a unique identifier for each device in a home network so that we can be found, and different pieces of data from the internet can be delivered to the respective device. So if I'm searching on my iPhone, my computer, I want, when I click search for a given website, I want the data to be returned to my IP address. And if we didn't have a way of distributing out that single IP address that our ISP had assigned our network, then all these searches would just be returned to the router, and it would have no idea how to find each of the devices on my network. So I have set up a little example here, and we're going to consider a case where our iPhone has an IP address of 192.168.22.87. Now this is a random example. I've just come up with this arbitrarily and it has no significance, but this would be a very realistic IP address for a given device in a home network. Now we can also assume that our ISP has assigned us a network address of 192.168.220 and a subnet mask of 255.255.255.0. Alright, so how are we going to calculate the space, the address space that our router has available to assign to different devices in our network? Remember, our ISP has assigned our router, or our entire network, a single IP address, and our router has to somehow take that one address and turn it into a bunch of different addresses that can identify each device in the network. So we're going to be looking at an example which is pretty practical. We've got this iPhone device. This might be one of your devices in your home network, and your ISP has assigned you a network address of 192.168.220 and a subnet mask of 255.255.255.0. And given these three numbers, or honestly just given the iPhone device and the subnet mask, we can calculate the entire address space that the router has available to assign to all the different devices. And here's how we're going to do this. We first need to convert each of these into binary notation, because this is going to be how we can conceptualize and convert into this address space. So we've converted the iPhone device and the subnet mask into binary. Now, using just these two addresses, we can calculate the network address that was given to us by our ISP. And the way that we do that is by looking at each of these bits, and if there is a 1 in both spaces, we'll put a 1, and if there's a 0 in either of the spaces, we'll put a 0. So you can see, using that sort of addition, or whatever you want to call it, we have come up with a resultant IP address of 110, and I'm not going to read it all, but you can see how this kind of works. We have 1s in both spaces here, so we have 1s, and then 0s in all these spaces, so 0s, and this is our resultant address. And lucky enough, if we convert this particular binary code into dot notation, we will actually get this network address that our ISP has assigned us. So there's actually something pretty interesting going on here with these numbers that may not be readily apparent by looking at them. And that is the concept of subnet masking, and how each IP address actually represents two different parts. So the first part of an IP address is going to identify the network within the world that your given device is sitting on. So as we remember, your ISP assigns your network just one IP address, and then that the router, or we're actually going to be talking about the DHCP server, is responsible for splitting that one IP address out into a bunch of different IP addresses for each device in the network. So how do we know which part of an IP address is going to be the network identifier? Well, that is where the subnet mask comes in, and the entire reason for a subnet mask is to tell the router how many different addresses it has available to assign to different devices. It wouldn't make sense for someone like me who only has maybe 5, maybe 6 different devices that I want to connect to my wireless network. It wouldn't make sense to give me like thousands of different IP addresses, because remember, we only have 4.2 billion addresses for the entire world population. So it would make sense for me to conserve the amount of IP addresses available, and therefore my internet service provider is going to set it up where I only have X amount of addresses. So this is how all of this resolves into the subnet mask. As we see here, we have a bunch of 255s, which basically means we have the first 24 bits of the subnet mask is 1s. And therefore, anywhere where you have a 1 is going to represent your network identifier. So this IP address that we have, we were looking at our iPhone device within the network. The 192.168.22 is going to be my network identifier. And when someone is searching for my computer, it's not very realistic, but maybe I was hosting like a web server or something, the first thing that they're going to do is figure out what network I'm sitting on. So it figures that out by combining the subnet mask with the given device, as we did here, and it figures out that the network that we're sitting on is going to be this one right here. And as you'll notice, this is the same exact number as this right here, and that is because the subnet mask, and the way we kind of add those together, is going to keep these the same, but then mask the last 8 bits of this iPhone device IP address and just turn them into a bunch of zeros. And that's basically how we're going to figure out how many devices we have available in a network. In this case, since we have 8 bits for the host identifier, or the devices, we have a total of 256 different IP addresses that we can assign within the network identified by these first 24 bits. Now, we don't actually have 256 different combinations, because there are 2 reserved addresses that are always going to be reserved. Number 1 is the network address, and number 2 is the broadcast address. So your network address is obviously going to be the identifier for your entire home network, and that's kind of how everyone's going to find you in the first place. Now the broadcast address It's kind of a complicated topic, but think of it as like a catch-all for all of your devices. And it's one way that the DHCP server, as we'll talk about later, is going to dynamically assign IP addresses to devices in your network. So in this case, we have 8 bits, so 256 minus the 2 reserved addresses. And so therefore, we can assign devices in our network addresses anywhere from, we're always going to have 192.168.22, and then we start at 1, which comes right after the network address, which is always 0, and we can go from 1 to 254, leaving the 255th address for the broadcast address. So basically, we can do anything from 192.168.22.1, or .2, or .3, 4, 5, 6, all the way up to 254, and those are all valid IP addresses for devices within my home network. And if you match up those IP addresses with the subnet mask, you're always going to get the network address as a result. So you can kind of see how by using the subnet mask, you can resolve everything that you would need to know about a given network. So we have figured out how many addresses are available, or the address space for a given home network, using subnet masking. But what we don't know is how the router goes about assigning these different addresses to your different devices as you add devices to the network. Now, the way that most routers are going to do this nowadays is using what we call a DHCP server, which stands for Dynamic Host Configuration Protocol, and is a modern way to dynamically assign IP addresses to different devices. And this is the reason why your computer's IP address is going to be changing. Like if you restart your computer, or maybe just every so often, it's going to be changed because of this DHCP server. Now on the screen, I've got my TP-Link dashboard. I've kind of grayed out the IP addresses for privacy, but you can see that I have the DHCP server setting on, and so therefore my router is acting as a DHCP server. So they're basically one and the same. You can think of a router and a DHCP server on a home network as the same thing. Now, it's going to be a little bit different for like corporate networks and stuff like that, but for our home network, just think of the DHCP server as the router. So, the router is going to assign these different addresses by using the address space that we had calculated before, and the way that it does this is like so. We're going to go through an example of maybe you're going over to your friend's house and you ask your friend, hey, what's your Wi-Fi password? And your friend gives it to you. So what you're going to do is open up your computer, type in the Wi-Fi password, and press enter. Now when you press enter, a semi-complex process actually happens behind the scenes. And this is kind of how that process plays out. First, it will check to make sure that your password is correct, obviously. And if it is correct, then it's going to identify your device by its MAC address. Now, this is not like Mac, like Apple computers. This is the Media Access Control, I believe. And this is a unique identifier that a manufacturer assigns to any physical device. So therefore, your computer has a unique MAC address, and that will never change. So that is how your computer is first identified by the router on the network once the password has been accepted. Once that happens, your computer is going to say, hey, Mr. DHCP server, can you let me on your network? Here's the password, make sure it's correct, and then the router, which we're considering as the DHCP server, is going to say, sure, here's an IP address you can use. You can use it for 120 minutes, and that is what we call a lease. So then your computer is going to say, well, only 120 minutes? I mean, I'm trying to watch a long movie here. Well, you'll be fine. It's going to renew as long as you're within range of the network. And this is really where the magic of this whole DHCP server comes in, because it sets these lease times. So when you go over to your friend's house, your computer is identified by its MAC address and goes through this little exchange and gets a temporary IP address. But when it leaves the network, it's going to, the lease that was given is going to expire. And since you're not in the network, it can't auto-renew. And therefore, the router or the DHCP server is going to say, oh, that computer or that device must have left for good. I'm going to take that IP address back into my little repository that I have available, and now I can assign this to different devices on the network. So when you leave your friend's house, you don't need to feel guilty that you're using up his IP address space. And as you remember, each home network only has maybe 256 different device combinations. So if every guest that came in the house took an IP address and left with it, you would run out of space to assign different devices and you'd be up against your limit. But with the DHCP server, it enables it to kind of conserve those addresses and dynamically assign them as devices enter and leave the network. So hopefully this was a pretty high-level overview for you for home networks, IP addressing, subnet masking, and DHCP servers. If you liked it, be sure to give the video a thumbs up and consider subscribing if you like these kind of videos. Until next time, I will see you later.